Hello! In this video, I'd like to give you some sort of intuition as to why the chain rule holds and how we can think about it. To start with, I want to start thinking about derivatives in terms of this idea of plugging in a range of values into a function. So here, this interactive allows us to take a function, in this case g of x is equal to x squared. You can type in whatever function you want, but we like the function g of x is equal to x squared, so we'll work with that. We have some sort of function, and we have a range of x values. In this case, the range from 1 to 3. And what we're going to do is we're going to take all of those different x values and we're going to plug them into our function. So if we plug in all of the numbers from 1 to 3 into the function y is equal to x squared, into the squaring function, the range of values for the output is going to be the numbers from 1 to 9. And we can see that here with these lines. We see filled in the range of numbers from 1 to 9. And this way of thinking about functions, this should seem familiar. We talked about before this idea of as we narrow in the range of x values, we can pay attention to what's happening with the range of y values. Ideally, it should be narrowing in on a particular value. With limits, you want to ignore what's happening actually at the point in this case 2. We just want to imagine plugging in values that are nearby 2 on both sides. And we see that as we narrow in this range of values on the number 2, the range of values for the outputs is narrowing in on the number 4. And so that tells us that the limit as x approaches 2 of x squared is equal to 4. And that's not surprising. And we saw some circumstances where, as we narrowed in the input values, the output values weren't narrowing in on one particular number, or maybe they weren't narrowing in at all, or maybe they were going off to infinity. There were lots of different things that could happen that could go wrong in terms of limits. That we could see thinking about things in terms of narrowing in a range of x values and looking at the corresponding y values and hoping that they narrowed in on a particular number. If they did, that was our limit. If they didn't, then the limit didn't exist. Now, this is actually a really useful way of thinking about real-world measurements and doing math with real-world numbers. For instance, suppose that we have some sort of part. So here I have just a plastic rod, and suppose I want to measure its length. Well, here I have a ruler, and line up the beginning of the rod with the beginning of the ruler, and we zoom in and make sure it's lined up properly. And as we can see, it's a little bit hard to see with the camera here, but as we can see, the end of this plastic part falls pretty close to one of the lines on the ruler. We could use that line marker as a kind of an estimate of the length of this part. But if we wanted to speak exactly, we could say that it falls in between two of the lines on this ruler, right? And so what that gives us is it gives us a range of values, right? Saying that the length of the part is between this value and this value gives us a range of values that we know that the length of the part falls into exactly. And so this is a really useful thing to be thinking about when you're doing real-world problems involving real-world measurements, so engineering problems, where you know that some value falls within a particular range, but you're not sure exactly what that value is exactly. And this is the case anytime you make a real-world measurement. You know that the real-world value falls within a particular range, but you're not sure exactly where it falls. And so we can represent this in terms of our graph as plugging in a range of values, right? We don't know which of these values the input is, but that tells us that the output is going to fall somewhere within this range of outputs for the y value. And this doesn't have to be just making real-world measurements. We can also think about this in terms of rounding, right? When I take pi and I round it to 3.14, what I'm really saying is that pi is somewhere between 3.14 and 3.15, right? That's what it means for it to when you cut off the decimals, it goes to 3.14. And what that means is that we have this range that we know that pi falls into. And so if we take that entire range, 3.14 to 3.15, and plug it into, say, the x squared function, the range of outputs that we're going to get is going to represent a range that contains the actual value of pi squared, and we're not really sure where in that range pi squared falls exactly, but we know that that range contains pi squared. And so there's lots of sorts of circumstances where you want to think about, we have some level of uncertainty in a value, right? We know that the length of this part falls within this range. We know that pi falls within this range. We know that the results of this calculation falls within this range. And to be able to think about doing mathematics with these ranges, this is a very common thing for engineers to think about when they deal with real-world numbers, is to think about taking ranges of values and applying math to them. Applying, in this case, the x squared function, although you can do more interesting things than just applying the x squared function. So this is a really concrete, really useful way of thinking about functions. And it's not just related to the idea of limits, it's also related to the idea of derivatives. Let's zoom in on this function here. And of course, this is something that we're familiar with happening. As we zoom in on a function, the graph of the function winds up looking a lot like a perfectly straight line. It's not perfectly straight here. It's a little bit hard to see, but it's not quite a perfectly straight line at this level of zooming, but it looks pretty close. And we know what the slope of that line is, right? The idea is that the slope of our original graph, y is equal to x squared, the slope of that graph at any one particular point, we take the derivative and we plug in that particular x value. So here our original function was, again, y equals x squared. We take the derivative, that's going to give us 2x. We plug in x is equal to 2 because that's where we are on the graph. We're at x is equal to 2. And that tells us that the slope, when we zoom in, is going to be approximately 4. Well, the slope is going to be exactly 4, but it's going to be approximately a line. And we can see that here if we count up the boxes. So in this case, going from this point here to this point here, the rise over the run is 4 boxes over 1 box, or if we want to be precise, because we've zoomed in, each box is 0.1 units on a side. So this is actually a rise of about, it doesn't work out perfectly, a rise of about 0.4 and a run of about 0.1. And so we take that ratio, and that gives us 4, and that's the slope. That's the derivative that we calculated. And then if we want to go over this entire range from here to here, when we calculate the rise over the run, well, that's going to be the length of this output range divided by, right, so the length of this output range, the height of that output range, is the rise going from this point to this point. And then the length of the input range is the run going from this point to this point. And so the ratio of those two, this range here is going to be 4 times as big as this range here. So the output range of values, the output interval of values, is 4 times as big as the input range of values, the input interval of values. And that 4 is the slope here, right? It's the slope of the function at this particular point. So one way to think about this is that 4, the derivative of the function, is kind of this multiplier. It multiplies the width, and the width of this interval really represents our uncertainty in this input value, right? When we were making measurements, we knew that a value fell within this range, and the smaller that range was, the more certainty we had, the more precision that we had, the more decimal digits we had. And as this range gets narrower and narrower, that represents us getting more and more confident, more and more information about the input value to this function, right? If we think about this in terms of rounding, it might be that we're getting more decimal digits, and so the range of values that we know that this thing falls into goes from, going from 3.14 to 3.15 to going from 3.141 to 3.142, right? As we kind of narrow that range in as we get more decimal digits. When we narrow in close enough, and let's narrow in again for a moment to narrow in on the range from, so this time we've zoomed in by a factor of 10. We're going between 1.99 and 2.01 for our range of inputs. And because we've zoomed in by a factor of 10, the y equals x squared, the original graph here, looks even more like a line, and the ratio of this rise over run, this size of the output interval over the size of the input interval, it gets even closer to the exact value of 4. So what we're really talking about here is that the derivative kind of represents a multiplier. It represents a multiplier of our uncertainty, of the potential error in these values, right? You can think about this as, well, we know that the value, we think that the value is 2, but we might be off by at most 0.1, right? So that's kind of our error, is this width of the interval. And this 4, the derivative here, is a multiplier for that error, right? The width of this input interval gets multiplied by 4. It's multiplied by the derivative. And this approximation, this is only an approximation. This approximation gets better and better and better the more we zoom in. It's not actually that good of an approximation when we go back out to this case where we were looking at the range from 1 to 3. It's not a great approximation for the ratio of the size of this output interval to the size of this input interval. Okay, so that's one way to think about derivatives, is this ratio of the size of the output interval over the size of the input interval. Now, let's imagine we actually want to run this through 2 functions here. So we want to take our value between 1 and 3, and we want to run it through first this g of x function, g of x is equal to x squared, and then we want to take the result and run it through another function. In this case, f of x is equal to 1 over x. So here we have the graph of f of x is equal to 1 over x, and what this interactive has done is it's taken this range of, let's see if I can get this to line up perfectly, it's taken this range of output values and imagined plugging in all of those different output values into the function f of x is equal to 1 over x. So we're taking our results from our g of x, and we're plugging them into f. And what this is really saying is we're looking at f of g of x, right? We're taking the results of g of x, plugging them into f. That's the same as saying f of g of x, right? The g of x is on the inside, it happens first, and the f of x is on the outside, it happens second. So this first graph is our graph of g of x, and the second graph is our graph of f of x. And what we see is that when we take this range of numbers from 1 to 3, plug it into x squared, we get the range of numbers from 1 to 9, and then when we plug that into 1 over x, we get the range of numbers from well, let's go from smallest to largest, because that's usually how you talk about ranges. It actually is the range of 1/9 to 1. So that's the range of possible output values that we get when we're talking about when we plug this into the function 1 over x. Okay, so again, let's zoom in. Let's zoom in our range of input values to talk about the range from, let's just do the range from 1.9 to 2.1. The range of y values that we get when we plug this in, it's going to go from 1.9 squared is about 3.6. I think it's exactly 3.61. And then 2.1 squared is 4.41. So we see this range of output values from our x squared function when we try to plug in the range from 1.9 to 2.1. And now when we plug in that range, so the width of this interval got multiplied by a factor of roughly 4, not perfectly, but roughly got multiplied by a factor of 4. And then over here, we have the width of this interval gets multiplied by a factor of the derivative of this function here. So what is this function? This function is f of x is equal to 1 over x. Remember that the derivative of that, you can think of 1 over x as x to the minus first. So the derivative of that is going to be negative 1 x to the minus 2. So if we think about that, let me make some notes so that we can see what's going on exactly. There we go. So f prime of x is going to be equal to negative 1, or just negative x to the minus 2, or negative 1 over x squared. So the slope of this graph here at this point is going to be negative 1 over 4 squared. So that's going to be negative 1/16. And it's a very shallow graph, as we can see here. And the width of this range here is going to get multiplied by that slope, just like we saw how the width of this range got multiplied by, right, the width of the input got multiplied by the slope to give us the size of the output. Here, the size of the input is going to get multiplied by the slope, and the slope here is approximately, well, I say the slope is exactly, but it's approximately a line. The slope here is going to be, let's see, f prime of 4 is going to be negative 1/16. So the size of this input range here, which is the output range from over here, the size of this input range gets multiplied by negative 1/16, and that negative just flips it. It flips, you know, we see that the smaller inputs are giving us larger outputs, and the larger inputs are giving us smaller outputs. But the size of that range is getting multiplied by 1/16. So here, the size is approximately 0.8 coming in, and we see that the size of the output is approximately 0.05, right, which is 0.8 times 1/16, giving us this output here. And we can see that as we zoom in further on this graph, and zoom in further on this graph, the approximations get better, right? So when we zoomed in to by a factor of 10 to go from 1.99 to 2.01, we see that this range is very close to going from 3.96 to 4.04. It's very close to just multiplying the width of this range by a factor of 4. And then we see that when we zoom in here, we're taking that range, and it's going to be even closer to taking the size of this range, the size of this interval here, and multiplying it by a factor of 1/16 to get the size of this output range here. Right, so that's the idea, is that whenever we apply the function, the width of this interval gets multiplied by the derivative around the center of the interval, and this approximation gets better the more we zoom in. And so if we think about this in terms of the actual composition of these functions, right? So when we compose these two functions together, when we take f of g of x, what we're imagining is we're plugging in points from this range. They're going to run through, remember that this first graph here is our graph of g of x. We're going to run these values through this function here. We're going to get some range of values. We're going to take that range of values and plug it into our f of x function and get some range of values. And the result is that we're taking this and we're running it through our function. We're running it through both functions in this graph here. So we're just going directly from this range of input values to this range of output values. We're going directly without kind of going through this intermediate phase here, but we're applying first this function g of x and then this function f of x to the result, and that's what we get here. Of course, the range of output values, the size of that range, well, first it gets multiplied by 4. First it gets multiplied by so this here is g prime of 2, right? This multiplier, this 4 that we're multiplying by is our g prime of 2, and then the size of this range gets multiplied by f prime of 4. And this f prime of 4 is specifically f prime of g of 2, right? The reason why we're looking around the number 4 is because 4 is g of 2. It's what we get when we plug 2 in to our original function. And this f prime of g of 2 gives us our multiplier, gives us the size multiplier for these ranges. We're multiplying the size of this range by f prime of 4 or f prime of g of 2, which is, as we calculated, negative 1/16. And so the multiplier for here, going from this, the size of this original input to the size of this output, well, first we multiply the size by g prime of 2, and then we multiply the size by f prime of g of 2. And so the result is that the ratio, this size here, the size of this output, the size of this input, is going to be, let's write this out, the multiplier, the thing that we're multiplying by is f prime of g of 2 times g prime of 2. And that tells us the slope here, that tells us the ratio of the size of this input interval to the size of this output interval. And that's another way of saying the derivative of this composition, the derivative of this f of g of x at x is equal to 2. So this is f of g prime at 2, right? It's the derivative of the composition, the derivative of f of g at 2. And that, g prime of 2 in this case was equal to 4. F prime of g of 2 we decided was equal to 1/16. And so this multiplied gives us, 1/16 times 4, which is equal to 1/4. So that's our f of g prime of 2. We see that the size of this interval here gets multiplied by 1/4 to give us the size of this interval here, and, well, we interpret that multiplier as being the derivative of this graph here. This graph, again, remember, being the composition of our two functions, f of g. And this doesn't just work at 2, this works at any value. Right? So you can replace this 2 by x, because we can change up this 2 for whatever number we want, and we get that f of g prime of x is equal to f prime of g of x times g prime of x. So this is a really kind of clever way of interpreting the derivative, and from this, getting the chain rule is kind of this really intuitive thing, not just some abstract symbol manipulation thing, but as this really concrete, right, running through this function, takes this error and multiplies it by 4. So maybe we were really certain, but now we're a little bit less certain about what value this number falls into. We have a kind of a wider range that we think that the value falls into. And then we take this wider range and then we plug it into this other function, and then the size of that range gets multiplied by the derivative here, gets multiplied by, well, it gets multiplied by -1/16. So you have to be a little bit careful about keeping track of the signs of everything, but that's okay. It gets multiplied by -1/16. So we have, this potential range of error. It gets multiplied by -1/16, and that makes the range of error much, much smaller. And then if we're kind of going through both of them, if we're doing first g and then f, well, the result is that the size of this range, the level of uncertainty, is getting multiplied first by the derivative here and then by the derivative here to give us this result here, which, as we saw, gave us a value of 1/4. So the size of the range and the output on the composition is going to be multiplied by about 1/4.